number 19, excuse me, problem number 20. That's where we want to start on this one. Okay, problem number 20 asks us to determine the exact value of the cosine of 22.5 degrees. So I know that 22.5 is got to be half of some angle that I already know, because it's certainly not twice an angle that I already know. Okay, I mean, think about what angle would you double to get 22.5? Well, that's, a ridiculously small angle. We don't know that. So we've got 11.25. Well, who knows that angle? But we do know the following. We do know that if we take 22.5 and double it, we get 45. So therefore 45, put a little degree symbol up there, 45 divided by 2 is certainly 22.5. Now 45, that I know, that's an angle that that I can easily see on my unit circle. So what I want to do is I'm going to take this guy right here, and I want to talk about the half angle formula for cosine. And so my half angle is going to be equal to plus or minus the square root of 1 minus the cosine of this top angle, so 45, excuse me, 1 plus 45 degrees divided by 2. Now the rest of it is just computation. So this is 1 plus cosine at 45 is root 2 over 2. So this is 2 plus the square root of 2 over 2, which is going to be this is the square root of 2 over 2 over 2, which is 2 plus the square root of 2 over 4, which is 2 plus the square root of 2 divided by 2. Now the question is it positive or negative? But clearly the cosine at 22.5 degrees has got to be positive because it's in quadrant 1. So we can get rid of the negative out there, so we don't have to worry about it. So we're dealing with an angle that's positive. Excuse me, we're dealing with a cosine value that's positive. Okay, let's take a look at the next one. So now we're looking at problem 21. And it asks us to graph the cosine. Now we need to graph it between negative pi and pi. So we know, let's pick some values. We know at negative pi, the cosine value is negative 1. So this is negative 1, this is positive 1. We know that at 0, the cosine value is going to be up at positive 1. And we also know at pi, the cosine value will be back at negative 1. At negative pi, negative pi over 4, or not negative pi over 4, negative pi over 2, or positive 3 pi over 2, we're going to be at a value of 0. And also at pi over 2, we'll be at a value of 0. So when we connect the dots here, we've got our graph for our cosine. You can also verify that one on your calculator, so you might want to be able to do that. 22 asks us to graph the sine of theta minus pi over 4. So, and we need to graph that on an appropriate interval. So what I'm going to do is I'm going to graph out what sine is first. So the sine curve, I'll do it in yellow here. Let's go between, so sine goes between negative 1 and 1. We'll go to 2 pi here, so this is pi. This is pi over 2, 3 pi over 2. So remember, sine, the height value starts at 0. We go up, and we come back down like this. So there's the sine curve. Now the pi over 4 is going to be a shift. Okay, it's a phase shift, right? To the right because it's negative on the inside, so we're doing this opposite. So it's going to be to the right of pi over 4. So we need to move every point pi over 4 to the right. So if this is pi over 4, this is 3 pi over 4, okay, 5 pi over 4, 7 pi over 4, and 9 pi over 4. This point originally shifts over. This point shifts over. Okay, likewise with this point, with this point, and with this point. So this green graph right here, the green graph is the sine, is that guy right there, the sine of the quantity theta minus pi over 4. Determining amplitude, period, and phase shift for problem number 23. So my function h is equal to that. The value out here is the amplitude, absolute value of that guy. So our amplitude is the absolute value of 3, which is just 3. Remember, absolute value asks us how far away from 0 are we. The period, the standard period for cosine is 360 degrees, or 2 pi. So we divide that by the number in front of the theta. So this guy is going to be, it's going to have a period of pi, just pi. So what's happening here is that function is not only being stretched vertically, but it's also happening twice as quick as what it normally would. So it normally would take it 2 pi to do one full revolution. Now it's only taking us pi to do one revolution. So I like to think of that as it's definitely a horizontal shrink of the function, but I like to think about it as the function happening twice as fast as what it normally would. The last one is the phase shift. And the phase shift is, it would normally be pi over 3 to the right. So we look at it as a positive pi over 3. However, because everything's happening twice as fast, it's not going to start over at pi over 3. It's actually going to start at pi over 3 divided by the number in front of the theta value, which is 2. So it's going to be pi over 3 times a half, which is pi over 6. The other way you can look at getting the phase shift is to take this 2 and factor it out of what's here. So this is going to be theta minus pi over 6. So that's another way to look at getting your phase shift. Okay, let's take a look at problem 24. We need to figure out what is the sine, the arc sine, excuse me, of negative square root of 2 over 2. Okay, so here's the deal. There are an infinite amount of angles. Okay, so the input here is a real number, square root of 2 over 2. In fact, it's a real number between negative 1 and 1. The output is going to be an angle. Now, there's going to be an infinite amount of angles that have a sine value of negative square root of 2 over 2. In fact, if we look on the unit circle, okay, there's an angle here and an angle here. This one is at 5 pi over 4. This one is at 7 pi over 4. And both of those guys, both those angles, have a sine value that's negative square root of 2 over 2, meaning that this length coming down on the unit circle would be negative square root of 2 over 2, where the hypotenuse here is 1. Okay. Now, any other angle that is coterminal with either of those two angles will also have a sine value of negative square root of 2 over 2. So, but here's the thing. We're talking about arcsine over what I'm calling the natural range, but it's really over where we're defining arcsine, the output. Okay. Arcsine and arctangent are defined in quadrants 1 and 4. What I mean by that is the output values will be between quadrants 1 and 4. So we can only take angles that fall over here. So the only angle that falls over there is 7 pi over 4. Now, but here's the trick. 7 pi over 4, okay, the specific angles that we want to generate out have to be between positive pi over 2 and negative pi over 2. So I can't use 7 pi over 4. What I have to use is the same angle that is coterminal with that, but falls between pi over 2 and negative pi over 2, and that is negative pi over 4, or negative 45 degrees, if you want to think about it that way. So to solve this problem, again, there's a whole lot of solutions that we would think would naturally come out of an arcsine, but the problem is, since there's so many solutions that come out, it's not a function. So to define arcsine, which we would like to define it as a function, we need to restrict it between angle values. So another way to think about this is restrict it between angle values of negative pi over 2 and pi over 2. Well, the only angle that falls in that range that has a sine value of negative square root of 2 over 2 is negative pi over 4. Any other angle that you pick, here's 5 pi over 4, here's 7 pi over 4, here's, you just keep going. All those other guys fall outside of this desired area. So again, when you're working with arcsine and arctangent, you want to be between negative pi over 2 and pi over 2. When you're working with arccosine, it's between 0 and pi. So arccosine is between here and here. So between 0 and pi. So when I'm dealing with that, I want to be between 0 and pi. I need to find angles that fall in here. Okay, let's go ahead and take a look at, we can do one more. Let's look at 25. Problem number 25, let's grab a different color here. We need to evaluate the cosine of the arccosine at 1/2. So to do that, we do work on the inside first. So we need an angle between negative pi over 2 and pi over 2 that has a sine value of 1/2. Well, that's going to be at pi over 6. So pi over 6 is the only angle whose sine value is 1/2. It's between negative pi over 2 and pi over 2. So what I've got here is the cosine at pi over 6. And we know that the right-left movement at pi over 6 is square root of 3 over 2. So that's our solution.